Hello everyone. My name is Kallol Bhattacharya, and those who don't know me, I've spent around 25 years building solutions for Fortune 500 companies. And here I am with the first lecture on DSA, which is Data Structure and Algorithms. This will cover most of your university curriculum, and people who are interested beyond university curriculum can also join me. This is one of the first lectures of DSA, and we will cover the entire course starting from very basic concepts of stacks, queues, arrays, etc. And then we'll move into the advanced algorithm concepts. Be with me. I'm sure this journey is going to be excellent in terms of grasping the power of what modern algorithms can do. Thank you. Okay, so good afternoon, good evening, good morning, whenever you're watching this, wherever you're watching this. We are trying to cover module 1 of DSA through this video series. And this would be a series of 2 lectures to cover module 1, and then we'll use module 2, 3, and 4 where we'll cover in depth on the advanced algorithms of DSA, and that would be subsequent video series in this entire course of DSA. Starting with today's lesson, and which is on module 1. As I said, we will cover this in 2 parts. The first part will be the introduction part of it, which includes the basic terminologies, the elementary data organizations, the data structure operations, covering insertion, deletion, traversal, searching, sorting, etc. And then we will take certain questions which are typically asked in the university curriculum and try to solve them, so that you have a 360-degree view of what is being asked, what is being taught, and how to marry both. The core concepts that you see on the screen, the core concepts portion we will actually be covering at a later point in time. So that would be the second video of this particular series. So we will be covering this concept today, and it's going to be around an hour's lecture, and we will try to cover and explain in absolute details about what each of these syllabus terminologies mean as far as data structure is concerned. Moving on, so as I said, what we'll do is, for the first part of this module 1, we will talk about what is the definition of a data structure. We will cover the types of data structures. Typically, there are questions that come around the basic terminologies of data structures, so we will cover that also. And of course, data structure is not complete without operations on data structures, which we will try to also cover in the last part of this particular series. As I said, we'll also try to cover the university questions that typically get asked in any and every examinations pertaining to the topics that we actually go through in this session. So what exactly would be a data structure is what we are trying to cover now. Now, if you see the data structure definitions, then there are various terminologies, various sentences that you will see from various books that talk about data structures. What I'm trying to do here is marry the 2 words data and structure in order to give you the definition of data structure. Now, data is basically anything that is meaningful in the sense of the data carrying a meaning doesn't make it a data. Now, let me explain that in a better way. What I'm trying to say is that take any number, 20, or let's say 30, or let's say 35, or let's say 40, right? These numbers do not mean anything to you, or mean everything to you from various parlance, but it may not mean the same parlance to me. For example, you may say your age is 20. I may say 20 is the marks I got out of 30. So 75, I may say that this is my grandfather's age. You may say that this is the marks that you got out of 100. Right? So just giving me numbers doesn't make sense unless you give the context to that number. Similarly, if I take a series of letters, let's say Anna, then with Anna, what I'm trying to say is that I will treat Anna as a name. Somebody else may treat Anna as a company name. Someone else may treat Anna as a palindrome. So this doesn't have any specific meaning, which is very specific, and every person will interpret that Anna in the same manner. When such a thing happens that you don't know the context, you don't know the actual meaning of that particular series of letters or digits that you see, it actually constitutes a data. So that's what is a data. So we covered that a data from a definition standpoint. We also explained you the data. Now, what I'll try to do is, I'll try to now see if we can explain structure. So if you see this data, let's say 21, 32, 11, 79, 51, then all of this is having no context. It can be anything. It can be your marks, it can be ages, it can be your bank balance, it can be the number of seconds that is left in the next 5 minutes. It can be anything, right? Now, if I am trying to organize this data a bit more structured manner, if I am trying to organize it in an ascending order, then I will be organizing it like this. Now, when I do that, then I'm bringing a method to the randomness, which is basically creating what we call as a structure. So this becomes a structure for that data. I'm creating a structure around the data. I'm trying to group things together. I'm trying to create avenues through which I can create some logic of grouping data. I'm trying to create a logic for organizing the data. So arranging or organizing data in a systematic manner is what we call as a structure. What does it help with? It helps in identifying patterns. It helps in identifying or grouping similar elements that really make sense from the raw data. So that's what we are trying to do with the structure part of it. So this, when arranged, this random set of data, when arranged in a particular manner, either it is arranged through some pattern discovery, or it is arranged through some grouping, then we arrive at something that we call as a structure, right? So that's the definition of a structure. Now, that being said, a structure is not going to help you create something for the computer. What I mean to say is that when I'm taking a structure in mind, which is this 21, 32, 45, 77, 99, this organized data in ascending order is not helping me to create certain activities around this structure. Those activities, let's say, are insertion activities, right? I want to insert, let's say, some element here. I want to insert 69 here. Can I do that? I cannot do that when I just proclaim that I have a structure of data. Unless I have a mechanism to insert, an algorithm to insert, I will not be able to insert. Similarly, there will be deletion, there will be search, there will be merge, there will be update. All these operations would be difficult for us to do on a structure unless we define a computer system or a computer mechanism to actually do all of those activities. So what is a data structure then? So the definition of data structure would be that it is a programming concept that defines not only how the data is arranged in memory, but also how the operations can be efficiently performed on it. And it's not just about physical storage, it's also about how data is logically or mathematically grouped. What is logical grouping? Grouping people, let's say, grouping data, random data into a male and female population, random set of people into male and female population. So let's say I have a person called A, a person called Z, a person called P, a person called Q, and I am trying to group them into the male and female population. and let's say male is A, male is Q, and females are, let's say, Z and P. Then Z and P group together make the female group, and A and Q group together make the male group. What have I created? I have created a structure. Now, does this structure support these operations? If so, then I have converted this structure into something that basically gives me the programmatic access to this structure, and hence I can perform the operations of insertion, deletion, search, merge, and update on this structure, and hence we call it as a data structure. So the definition of data structure would be, it is a logical or mathematical model or a particular organization of data which supports specific operations like insertion, deletion, searching, and sorting. Now, the keywords here are actually logical and mathematical, and these two keywords are very, very important. Logical, I just now explained that we have grouped elements which are random, which are called data, into logical groups, and mathematical groups also we did. We took these random set of numbers and we organized them mathematically in ascending order. Right? So that's also something that we did. Now, while we have done that, that's basically structure for you. Does this structure offer these benefits? If these offer these benefits, then what you have created is actually called as data structure, which is basically nothing but a programming concept that defines not only how the data is arranged in memory, but also how the operations are being carried out in memory. So that's basically the definition of data structure that we are talking about right now. Now, what do we achieve by actually doing all of this? So if you see the concepts of data structures, which is basically, again, if I repeat, data structure is nothing but your a computer concept or a programming concept with which you can make mathematical and logical grouping of random set of data, and also support operations on those data which are in the tune of the inserts, updates, deletes of the world. Now, that being said, if we try to figure out what is the benefit that this data structure actually provides us with, then we will see that speed and space would be two benefits that it provides us. Let's talk about speed first. Let's say that in a room, I am expecting people to walk in by their heights. So people who are taller will walk in first, right? And people who are shorter will walk in at a different point in time, or at a later point in time. So if I might not have drawn it to scale, but what I'm trying to say is that this person is the tallest person, this person is the next tallest, this is the next tallest, this is the next tallest, and this is the next tallest, and this is the shortest person. Now, if I have arranged them in this order, which means the tallest person is on the right, and if this room is actually expecting this tallest person to enter, then the operations that the room will actually do with the tallest person is spot on, because the room had planned for the tallest person to be the first person in the queue, and accordingly had designed the set of things that they want to do with the person entering the room. Now, suppose that you don't do that, and the tallest person is here, and then we have a shortest person, then we have the next tallest person, and so on and so forth, right? So if this is the structure where we are actually having a random set of heights, right, and we are trying to enter the room, this person enters the room, do you think that inside the room, the person who is carrying out the activities on these people, whatever those activities could be, the entire plan will go for a toss, because he's expecting the tallest person has not entered the room. So the entire set of activities will go for a toss. And when this happens, then what are you losing out? You are actually losing out on time, because there will be a time adjustment that needs to be done by the person inside the room in order to make sure that he can accommodate with this particular queue. So instead of that, if he got this particular organized queue, then he would have been in a much better position as far as time is concerned. So what did we do? We organized the data here. We organized the data in a structure, right? So we organized the data in what structure? In a descending structure, descending order of height, right? So that was the organization that we did on that structure. And because we did it on that descending order of height, we are able to actually therefore process the data much faster, and hence that's the benefit that data structure gives back to you with. Let's talk about the data structure with respect to what the benefit the data structure gives with respect to space also. So from a space standpoint, when we talk about data structures, let me just clear the screen for you. So from a space standpoint, when we actually are talking about the data structure, then I would say that let's take that example, a classical example of let's say that we have defined an array, right? And in this array, what we have done is we have defined an array with 4 continuous positions. So we have, let's say, 7 here, 29 here, 0 here, and 79 here. This is my 0, 1, 2, and 3rd pocket. Now, here what we are trying to show you, or what I'm trying to show you, is that this particular array is occupying 4 bytes of memory per block of that array, and therefore is occupying 32 bytes of memory on a 4-byte integer array system, right? So obviously depending on the compiler and depending on the operating system, we can have 8 bytes for an integer also, but I'm considering a 4-byte computer system, and in that I'm saying that a 4-pocket array will actually consume, I'm sorry for that, this would be 16. So I'm saying that a 4-byte computer array system will actually consume 16 bytes of contiguous memory space. Now, do you think this memory is optimized? An integer, if it has to be represented, it needs 4 bytes, and the array is having 4 different integers. It uses contiguous memory spaces for 4 bytes. So it's a very compact structure, if I would so call it, that actually doesn't waste any space. Whatever is required for integer, it actually takes that for the integer, and actually creates a model by which it can actually traverse through these integers in a sufficiently scalable as well as speedy fashion, and it also makes sure that the space that is given in terms of the pocket size for that will be able to store any signed or unsigned integers. So that's what it ensures. Is there any optimum way for storing integers? Probably not. So that way, what we have done is we have taken some random set of data, we have organized the data in a particular fashion, whatever that fashion is. If there is a pattern here, then there is a pattern here. If there is no pattern here, it is still random. But we can of course create a pattern by sorting it by in an ascending order or in a descending order. And once that is done, then the array is a most optimum data structure in terms of storing an integer in contiguous memory locations, and that's what we have achieved here. So what did we achieve? We achieve that instead of going through the painful process of pointers and storing data for pointers, like if I have an array like this, and then I have a pointer variable also that is pointing to this, and then I move the pointer here, 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 then what are we doing? We are creating one more variable. So instead of that, what we are trying to say is, with a simple array, we can actually create a process, a structure in place, which will be very optimistic in terms of speed, as well as very optimistic in terms of space. So speed and space, these would be the 2 important dimensions that any data structure will achieve, which is what I'm trying to establish here. So moving on, our second topic for today would be the types of data structures, and this we will probably dwell some amount of time here. Now, the types of data structures, as you can see on the screen, will be mostly around 2 basic types, primitive and non-primitive, and we will cover all of these data structures as we go forward in our lectures. For now, the primitive data structures are the most basic forms of data that are provided by programming languages. So they would be typically primitive data structures around the int, char, float, double, which is basically atomic in nature. They can't be broken down further. They are understood directly by the programming languages, and those are your primitive data structures. They do not support insert, update, delete operations, and hence they are primitive. They are also primitive from the context that they are atomic data structures, and they do not have the capability of being contiguous or being called as a collection of integers, or a collection of floats, or collection of characters, right? So because that way, if you have to create a collection, you'll also have to create an array for it. But array is not a primitive data structure. What we are just talking about is basic primitive native data structures, which are atomic in nature and are fed directly to the programming languages, and they store single values, and they are the foundation of building more complex data structures. So that's your primitive data structures. And when you use such primitive data structures to build non-primitive data structures, basically you are bringing complex data structures. So we are talking about, let's say, structures, we are talking about arrays, we are talking about linked list, stacks, queues, trees, graph. Then basically that is your non-primitive data structures. Now, the non-primitive data structures are typically around these kind of concepts. Like, let's say, let's talk about an array, right? So an array is what? An array is something like this, where we are storing contiguously a similar type of a data. Now this array is created by an integer. Let's say I have an integer here, which means I should also have an integer here, I should also have an integer here, and so on. Which means, what am I doing? I am using primitive data structure. This is called primitive data structure to create what? A non-primitive data structure. So I have created an array which is a non-primitive data structure using primitive data structures. So that's what this means. Now, if that is understood, then primitive and in a non-primitive data structure world, we would also have something called as linked list, which is coming from structures, and we will cover that in details in our subsequent lectures. I'll not go to the details of it. We will have stacks. In stacks, you know that if you stack some plates like this, then this plate can only be taken out first, which means that the last plate that went in, last in, is the first out. That is LIFO. And if we actually flip the context of stacks and try to build a queue, then queue is like this, like people are standing, here is where they want to go, and this person came in first. So this person who came in first is the first person who goes out, first in, first out. And we will also study that concept as we move forward. And so we talked about the stack, and this is the queue that we talked about. There are graphs also. Before we proceed to graphs and what they are, what I wanted to touch upon is the fact that you have an array which basically allows you to move from left to right or right to left. That is, you will propagate from here by moving from this element to this element, and so on and so forth. Or you may also move from the right to left if a particular data structure allows you to move from right to left. And we will see that right to left movement when we talk about queues and we talk about circular lists. That is when we will see the right to left movement and the continuous movements of data structures. But what I'm trying to get at is that if you think about the movement of all of these data structures, then the movement of all of these data structures are in a linear manner, which means it goes from either left to right or it goes from right to left, right? So this is going to be always a linear data structure where you will be always trying to figure out that if I have to go to the next element, I can only go by one element at a time, from next to next to next to next to next, and so on and so forth. So the element which actually is your source will only have one path to actually go to your next element. So that is what is meant by a linear data structure. In case this element has multiple paths to go to the next element, then what we have created is something which is non-linear data structure. For example, a tree, right? So if this is a tree branch, If this is a tree branch, then from this branch I can go to this branch, or this branch. I have options. I need not necessarily be stuck to one single path. So which is what my tree will give me, and likewise my graph will also give me that. For example, from a node like this, and if there are so many places I have to visit, then I can go from here to here, or I can have any kind of connectivity to go from any node to any node. And therefore what I am creating is called a graph, and hence every node will have multiple options to reach every other node, and through this we can actually calculate my route, my path, etc. And we will cover this. We will cover graphs and trees in module 4 of our discussion. But for now, I'm just trying to limit this to the understanding of the types of data structures, and we have discussed all of that right now. We will just summarize it in the next 30 seconds. Integer, float, character, boolean are native data types, and they are primitive data structures. They do not support insert update operations. Non-primitive data structures are created from primitive data structures. They are complex in nature. If you create a data structure which moves in only one direction, where every node can only access the next node or the previous node, then we have something which is called as a linear data structure. And a non-linear data structure is when every node can access any node for that matter, and not necessarily the next node in the queue. That is basically a non-linear data structures. The examples are on your screen. So that's typically what we needed to discuss about the types of data structures. Now moving on to the next concept, which is on the basic terminologies of data structures. So if you see the screen and you see this data that is in front of you, now this data tells you that the entire set of information that you see on the screen is, I'm sure you can guess that it is about a student, right? So if this is about a student, does student represent something in the physical world? Does student represent something in the physical world? Is student a practical word or a practical actor in the real world? So definitely he is, or she is. So this is an actor in the real world, right? So this is an actor in the real world means this word student mimics the real world, mimics something in the real world, right? So what that means is that I have coined a word which is definitely existing in the real world, and it is not a fantasy word. It's something that definitely exists and is actually an actor in the real world, and hence I would call it as an entity, right? So what data, what we see on the screens is actually called as an entity on the screen, right? So what are the entities? Students are the entities. And what are those student entities? So this is one student entity. This is one student entity. This is another student entity. This is another student entity. So this is what we see on the screen, right, as entities. And what are those entities? As I said, these are students. Because they practically mimic something in the real world, they are called as entities. So for example, employee can be an entity. Buildings can be an entity. Parks can be an entity, and so on and so forth. Anything that you will find relevance, representation with the real world and is a noun is an entity. So that is what is the definition of this entity. Now what do you see if you were not given these roll number, name, marks? Then can you make anything head tail out of this data? You cannot, because these are again just some numbers, a random set of characters and numbers for you. So basically that is called as data, and we define that in the first part of this lecture. Now, if you see this column, this column, this column, then what we have is what we are calling as a field. Why? Because in this column, only one type of data is stored, which is an integer, which represents the marks of the entity student. Here, only one type of data is stored, which is basically the name of the student that is getting stored. Now, if that is clarified, that in my table, columns represent my field. So the field that we are talking about here is nothing but the columns here, and each of the field has a single type of data that it's supposed to store. It cannot store different types of data. As long as a column stores the same type of data, it is basically called a field. Now, if we take all the fields in a particular row and add them up together, we get what is called as a record. What is a record then? The record is the line, the row that actually represents each line of record. Each line of this particular table represents a record. So the rows are actually representation of records. Just to summarize, rows are records, fields are columns. Now, if we take from the record one item, then we get what is a data item. So that's what is a data item. So when we are considering the item without the record, we have not defined the record itself. We are just considering 103. It is still data. But when we have defined the item, or when we have defined the record, I have defined the record as this row, then any small field in that record is a data item. Right? So that's what is the difference between data and data item. Moving on, you have your entity sets next up, which is basically if this is an entity row, this is an entity row, this is an entity row, then series of more than one entity rows make up an entity set. Right? So that's what is an entity set. Now, if I have an entity set, then means I have some data, and this data, if I have to store somewhere, if this data have to store somewhere, I need something which is called as a file, a persistent storage medium. So that is the definition of a file, so that I can retrieve it whenever I want, I can write to it whenever I want. Now, if you see this column marks, and which is the field, we have already understood that this is called field, and it contains similar kind of data. In this case, it contains marks. So if you see this marks, then you will see that this marks data definitely will have a smaller range and a larger range, smaller value and a larger value, which basically creates a range. So marks can be valid from 0 to, let's say, 100. So what have we created? We have created a range, right? So range of valid values for a field is called a range. Valid values for a field is called a range. Can you interpret this table now? You have understood this is my field, which is the column. It has the same type of data. This is my record, which is the row. It has records of an entity. If I pick up any item from that record, it becomes a data item. Every column has a range. So this column has a range that it can be between, let's say, 3 digits. That means it can be from let's say 100 is what I am starting my digits from, and it will go till 999. So that is my range. But then from all of this, can we interpret something? Can we say Priya stood first? If we can say Priya stood first, then what we have is called as information. That is the information we are trying or we are getting from this particular data set or an entity set, right? And of course, if I ask you to figure out if we can extract data like this, let's say I have so many students and their marks are 85, 92, 75, 85, 87, 69. I have more students, not just these 3, right? So I have more students here. Now, can you tell me that if I say, give me all the students whose marks is 85, how many records will it return? Don't you think it will return this record and this record? That means it will return more than one record, right? However, if I say that give me all the students with roll number, let's say 102, then don't you think that it will return only this record? Right? So roll numbers cannot be unique. Roll numbers cannot be duplicated. It is unique rather. Right? So when something returns a unique record for you, right, from an entity set, that particular field is called a primary key. So that is on your primary key. The last two definitions that are part of your basic terminologies of DSA are fixed length record and variable length record. And it's easy to understand because let us assume that roll number is 3 digits, name is, let's say, 10 digits, and marks is 3 digits. So this is my 4 bytes, 4 bytes, 4 bytes. Actually not. While they are digits, we are considering them as one single integer, right? So of course, this would be 4 bytes of memory, but they will consume only 3 digits. And this will be 10 bytes of memory for 10 characters, and this will be again 4 bytes of memory for your marks. So no matter what, you will be consuming for every record these 18 bytes of memory. For every record, you will be considering 18 bytes. So this will be 18 bytes, this will be 18 bytes, this will be 18 bytes, and so on. Right? Now compare it with a system where, and this is called as a fixed length record, by the way. And compare it with a system where I'm saying that no, if I have a name which is 6 letters, then while I will take 4 bytes to represent my roll number of 3 digits, let's say 101. So I will take 4 bytes here. I will still need only 6 bytes of memory to represent the name. I will not take 10 bytes. I will only take the number of bytes of memory that I have that is needed particularly. Here, even if I had the word, my name is, let's say, Kallol, right? So if I say Kallol, it will still have used this space, this space, this space, and this space. However, here, if I say Kallol, right, it will only consume those 6 bytes of memory, right? So if the other name is, let's say, Rahim, Rahim, it will only consume 5 bytes of memory. So it is adjusting itself from a variable memory standpoint in terms of the data that you have, and that is getting basically added up to create the variable length record for you. So if you have records where the size of the record is dependent on the values that you are putting in the particular fields of that record, then it's called variable length record. And if you have a record which is always going to be the same size, irrespective of the values that you put, then it is called a fixed length record. So that is on the basic terminologies. Now coming to the operations on data structures, I'm sure you are aware of the operations, but I'll just quickly glance through this, and then we will probably be wrapping this session up with the most common questions that are asked. So if you consider a data structure, as I said, data structure is, I'll just recap data structure again. So we said data structure is, there are 2 things to a data structure. One, it should be organized set of data in either a mathematical manner, which is ascending descending order, or in a logical manner, like the gender example that I gave you to organize data. You can do that. You can organize people by their skin color. You can organize people by their ethnicity, etc., etc. That's also a logical way of organizing data. And the data that you have created should support the insert, the update, the delete, the sort, the search, the merge, and the traverse operations. These operations should be supported. All of these operations are listed here. So unless this particular thing is satisfied, you do not have a data structure, right? You may have a structure, but you do not have a data structure, right? So that is what I'm trying to probably convey here. Now, when you say insert, then insert actually means if I have an array like this, if I have an array which is 4, 5, 6, 1, and I want to insert here 7, then what am I going to do? I'm going to create a fresh array, and I'm going to insert the 7 after copying the other elements of the array. So I'll copy 4, 5, and then I'll put 7, and then I'll put 6 and 1. Right? So this is my insert operation. So an array supports an insert operation is what we just now see. Right? Moving on to the next one, update operation. Let's say I want to update this particular record, the 7th record, to something which is 10. Then I will just position myself in terms of the index position. So if this is 0, this is 1, this is 2. And if my array is called ARR, I will just say ARR of 2 is equal to 10. Now, if that is understandable, then we move to the next one, which is your delete operation. Now I want to, let's say, delete this particular element. Then what I will do, I will create another array and I will delete, I will put this, but I will not put the deleted element. I'll put the next element, which is 7. Then I'll put the next element, which is 6. Then I'll put the next element, which is 1. Right? So that's how I will delete by creating a new array. Next, what I'll do is, if I have to sort, then this particular array I will sort by using various sorting techniques. And I could use a bubble sort, I could use anything for that matter. So I will basically be reaching at something which is looking like this: 1, 4, 6, 7. After my sort is done, it should look like this. If I want to search for an element, let's say 6, then it should return me with 2, basically, which means the index position of the array where I can find out the element 6. So this is 0, 1, 2, 3. So on the index position 2, my 6th element is residing. So I have successfully searched for the element 6. So that's your search operation. We also have merge. Merge is basically taking two arrays and merging them together. So you can have two arrays like this. One array looks like this, 3, 9, 0. Another array looks like this, 6, 5, 1. And you can merge these by creating a fresh array and copying both the arrays into this fresh array. So you can say 3, 9, 0, 6, 5, 1. Right? So that's your merge operation. Traverse operation is when I run a loop and start printing each element that I encounter. And that is called as traverse operation. It could be printing, I could be doing any operations on it, not necessarily printing, but it means actually going through each and every element of the array through a traversal algorithm and doing whatever the operation I'm supposed to do. So these I explained in terms of an array, but this is applicable to any and every data structure that we are going to study. Because as I said, the second property of a data structure is that it should support all of these operations. So all the data structures that we'll cover in this lecture will be supporting all of these operations. I just gave you an example with arrays. With that, we are done with the theoretical part of the lecture, and we'll now try to cover up some common questions, and we should be able to wrap up in the next 15 minutes after covering these common questions. As I said, this is part 1 of the module 1 lecture. Part 2 will be coming up in the next couple of days. So watch out for that announcement. But let's start solving these one at a time. What is the disadvantage of an array data structure? Now, of course, array is a data structure, but it will definitely have some advantages and disadvantages. We are talking about disadvantages here. The amount of memory should be allocated. To be allocated should be known beforehand. Of course, it should be. If I define an array, I cannot keep it blank like this. I need to say something. That means I am instructing the compiler that please give me 20 pockets of memory. And this is a static array. We are not talking about dynamic arrays. So the amount of memory to be allocated should be known beforehand. Yes, this is true. But so this could be the answer, but are the others? Let us check. Elements of an array can be accessed in constant time. No. The elements of an array, disadvantage, we are talking about disadvantage. Now, the elements of an array can be accessed in constant time is not a disadvantage. Why? Because the elements of an array that can be accessed in constant time, because I can actually use my index mechanism to access this, it's never a disadvantage. So I can directly go to this particular element by using ARR of, let's say, 17. So it's not that because it is constant time. Constant time means for accessing any event, you will need the constant CPU cycles, because you'll use the index method and you can actually access any element for that matter in the same constant time. Is that a disadvantage? Of course, it's not a disadvantage, right? So this definitely cannot be a disadvantage. Elements are stored in contiguous memory block. Of course, that is an advantage because we can use pointer arithmetic to actually navigate. So in an array, contiguous memory block access is not a disadvantage at all. And multiple other data structures can be implemented using arrays. Of course, we can create a structure and then we can create an array of that structure, right? So we can create multiple other data structures using arrays. So definitely this one will be your correct answer, right? So moving on to the next question. How are strings represented in memory in C? We know that strings are definitely going to be represented as an array of characters, which is, let's say, str, this, and we can actually keep hello in str. What will happen is, in the array portion of str, we will have something like this. We will have H, E, L, L, O, null, right? So that's how the string will be stored. I hope you are understanding null terminator. I will not go to that, but that's how the string is actually stored in memory. So it's an array of characters. I don't think we need to see the rest of the options, because string in C is definitely an array of characters. Now, if the elements of a data structure are stored sequentially, then it is what? If the elements of a data structure are stored sequentially, then we already have discussed this. Then we have something which we call as the linear data structure, where sequential storage actually means that you are actually creating a data structure where from one element you only know the position of the next element and the next element. From this element there can be only one traversal path to the next element. Of course, you can access an array from outside using an index. We are not talking that. We are saying that if you are here, how many paths do you have from here to move? You can only move by moving to the right or moving to the left, right? You cannot move you have only one option, right? Either in the forward direction or in the reverse direction. You do not have options like this, that from this you can go to any direction, right? So you do not have this kind of an option. From here you can go to any direction, but that's not what we are talking about. Elements of data are stored sequentially, then it is called a linear data structure, right? So if we have a sequential storage like this in array, right, we will have something called as a sequential data structure. Now the next question is about malloc, and malloc we had studied in C. So what is it? It's actually a pointer of type. It's malloc basically returns a void pointer. This is the answer, but let me explain you that answer. So what happens is, you are asking malloc to memory alloc or memory allocate. The syntax is saying that it wants you to give it the size of what you want to allocate. So typically what people do is, they say, okay, if I need 5 integers, then I will say 5 multiplied by the size of an integer, and that's what I will ask malloc to allocate me as the size. So malloc will go into the memory and it will allocate 5 bytes of memory for you. So this will be 1 byte, which 5 integer pockets for you, and each integer pocket will be typically 4 bytes in a 4-byte computer system for integers, and we will have 4, 4, 4, 4, 4 is the total number of bytes, which is 5 multiplied by 4, which is 20 bytes of memory will be allocated for you. Now, can you say that this syntax is the same as this? Of course we can say, right? Because this is nothing but an expression. So this expression will evaluate to this. Now forget about this syntax. Now from this particular syntax, if both the syntaxes are same, Does malloc know that you wanted to allocate 5 integers? 20 can be 20 characters also, like this. Maybe you want 20 characters of space, 1 byte each, right? So how does malloc know? How does malloc know that you want memory for integers or memory for characters? It doesn't know and it doesn't care. All it does is that it returns this as a void pointer. This address, it returns it as a void pointer. This address, it returns it as a pointer. But it doesn't know what kind of pointer it is. While it is a pointer, it doesn't know the data type of the pointer. So it keeps it as void, because it doesn't know what you are going to do with that data, right? So malloc will always return a void pointer. Now what we typically do is that because we know we are wanting to store integers, we will say void pointer, please convert to int pointer, and I will store it inside a int pointer. This is what we typically do when it comes to malloc, right? So we will create an int star ptr equal to int star malloc 20. Why? Because malloc actually returns a void pointer, because it doesn't care or doesn't know what kind of data you are storing. So it will always return a void pointer. So that's the answer to this question. The next is on a data structure. A data structure is a particular way of organizing and storing data, right? So we are both organizing data and storing data in the computer's memory. See, whenever you have the word data structure, you will see the word computer, because otherwise it is a structure. As long as you are taking the structure and trying to put it inside of a computer system, you are creating avenues for the operations on the data structure. You are creating avenues for storage of the data structure, and you are creating avenues for organization of the data structure, of the structure rather, and therefore you are creating what we call as a data structure, right? So that is what the data structure, particularly this particular fill in the blanks, hints towards. Okay, so the next question is around column major matrix. So I think we would not have covered this topic in the last few sessions that you might have undergone in your universities. In case it has not been covered, let me cover a column major matrix and what it is, and let me try to explain you before I solve this problem for you. Now I'll spend some more time here, because there are other problems related to this. So there's going to be a need to probably spend more time, be more informative, and be more explanatory in terms of what a column major matrix is. Let me draw a matrix for you, and then we will take it from there. So if you see this matrix that we are trying to draw, right? So I'm trying to draw a, let's say, 4x3 matrix, or let's say a 4x5 matrix for that matter, right? So this particular dimension is your dimension of M, and this particular dimension is your dimension of N, which is your columns, right? So this is your rows, M is your rows, and N is your columns. So this is what we mean when we say an M by N matrix. Now in this M by N matrix, if we name it from a zero index standpoint, then this becomes 0, 1, 2, 3, 4, and this becomes 0, 1, 2, 3, right? So that's your zero index nomenclature. Now in this nomenclature, if we have to figure out how these this column matrix is actually stored in memory, then first of all we'll have to understand that how a 1D array is stored in memory. So if we take this 1D array like this, right, and if we say that this 1D array is int arr 5, right, and in that arr 5 I have 7, 8, 10, 5, 9, then this arr is stored in memory in contiguous memory blocks, and each of these are addressed by indexes, and each of these have their own addresses. So this has an address of, let's say, 4000, this has an address of, let's say, 4004, considering a 4-byte integer system, right? So where am I getting at is that if I know that I have a 1D array, then I know that for sure the 1D array will be stored like this, one after the other, because you have one dimension and it's very easy to traverse in one dimension in memory. But now you actually have 2 dimensions, one dimension here, one dimension here. How will you store this entire 2 dimension in a structure like this, right? So there has to be some rules in place for that, and that's what I'm trying to get at. So the rule that we will follow is that it's already said that we are in a column major form. So what does column major form mean? Column major form means that we are going to go by the columns. We'll go like this, then we'll go up, then we'll come down by this, then we'll go up and come down by this, and then and so on and so forth. So what will happen is, if I draw the memory map here, right, so it will look like this. We will first take the first element, which is 0, 0, right, and the next element will go down, which is 1, 0. Then it becomes 2, 0, 3, 0, 4, 0. Then we will reset the row. We will make it as 0, 1, 1, 1, 2, 1, 3, 1, 4, 1. We'll reset again. Then we will say 0, 2, 1, 2, 2, 2, 3, 2, and 4, 2. We'll reset again. We will say 0, 3, 1, 3, 2, 3, 3, 3, and 4, 3. So that's what we will do. Now here, when we have done this, because we are in an index-based position of 0, that means we are in a 0 index-based position. So this item is 0, 1, 2, 3. This is how we will contiguously stored and contiguously accessed. So this is the second 2 dimensions, first dimension and second dimension, which is contiguously stored in a column major fashion in memory, so that you have no problems at all to access these elements, right? So I have 20 elements, 19 indexes, and they are structured like this. So if I say this particular column, don't you think this particular column is this? Of course, yes. Then the second column is this, third column is this, and the fourth column is this. So that is how it is stored by columns, hence it is called as column major. Now if I have to access, let's say, an element like this, right? So how will I access this element? So what I will do is, can we appreciate the fact that we are skipping 2 columns before we even reach this column? So to reach this column, we'll have to come from here, skip this column, then we'll have to come from here and skip this column also, and then finally we enter our column of interest, and in that column of interest we'll have to skip certain rows to reach here. So what are we skipping? We are skipping 2 columns, right? So if we are skipping 2 columns, where is this 2 going to come from? So let us figure that out. What do we have? We have M, we have N. What is my M? My M is actually 5, my N is actually 4. So we have a 5 cross 4 matrix. And what is this element? This element is 1, 2. So we are trying to access an element which is at 1, 2, right? That means let us take I as 1, J as 2. Now if we know that this 1, 2 element is here, right? So this 1, 2 element is here, then our life becomes simpler by saying that we will skip 11 positions to access this 1, 2 element, right? So if we have to do that skip 11 positions, what is the formula that we can write? Forgetting about the formula for now, if we agree that we are skipping 2 columns, where is this 2 columns going to come from? So if you see that we are talking about columns, which means that we will have to talk about J, right? So we will have to talk about J, and that J will help us to skip the columns. So we will say that we will take J and multiply it That means 2 columns have to be skipped, but in each column we'll have to skip so many rows. And where is that rows going to come from? My M. My M will say how many rows. So how many elements are there to skip? That many number of rows. So we will have to skip M elements. How many times? J times, that is 2 times. So we'll have to skip 5 elements 2 times, right? And then we reach at 10th position, which is here, but we have to reach here. So we will have to add one more, and that one more is going to come from your I, because we are now going down the row, one row at a time. So we will go to the row qualifier, which is our I, and say I, what is your value? I will add it to me. So this will be 10 plus I. So 10 plus 1 will be 11, and we have our answer. So this answer will be practically applicable for this particular problem. But if we see that, so the problem becomes M plus J plus I, but M plus J plus I is not a solution here. There is M plus J minus 1 plus I, right? So in order to reach that, definitely this particular solution will not work. And the reason I explain this solution is because it's the most common solution. But when such a thing happens, we'll have to shift to a one index based system rather than a 0 index based system. So what we'll do is we'll take the same example and we'll move on to a 0 index based system. So we had what? We had 5 rows, and we had 4 columns. So now we'll do a 1 index based system, right? So this is a 1 index based system for the same thing. Now if I do a 1 index based system, how does my memory map look like, right? It will look like the same, but remember we are doing column major. So we are traversing these columns, and then only we can reach to this element. So our element still remains the same. It is here. We are trying to access this element. So what will we do to access this element? Let us write the memory map first. So we have 1 1, 2 1, 3 1, 4 1, 5 1. Then we have 1 2, 2 2, 3 2, 4 2, 5 2. Then we have 1 3, 2 3, 3 3, 4 3, 5 3. And then we have 1 4, 2 4, 3 4, 4 4, 5 4. Right? And if I just name this now in terms of their index positions, because we are at the index position of 1, so we will start from 1, and this is what we will get: 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Right? So what do we have as our position? 2, 3. So what is our M? Our M is at 5, N is at 4, I is actually 2, J is actually 3. That is the elements that we have to access. And how many, if we have to access this particular element, then this is at 2 and 3. That means 2, 3. So where do we have 2, 3 here? Here. So we have 2, 3 here, and that means we'll have to go to position number 12. How do we create position number 12 through some formula is what we have to see. First of all, we are skipping 2 columns, right? So where are those 2 columns going to come from? We will take the help of J, because J helps us with columns, right? So J is 3, but I need 2, so I need J minus 1. And then how many rows are we skipping in each column, right? So 2 columns we are skipping, but 2 columns are skipping, we are fine. Each column we are skipping 5 elements. So that 5 elements is coming from our M. So we will say M star J minus 1. That means how much? M star J minus 1 is 5 into 2, which is 10. and I have to reach 12. So I have to add 2 to it. Where is this 2 going to come from? 2 will come from here, right? So that is what will happen as far as this particular sum is concerned. So it will be plus I, right? M star j plus 1 plus I is the answer. So this is the answer for this particular problem from a column major standpoint in a one index basis, right? So that's the answer. I hope this is understandable. Now let us move on to the next part of the problem. Differentiate between linear and non-linear data structures. Okay, so if we have to differentiate a linear and non-linear data structures, we have already talked about it at some point in time in this lecture, and what we are trying to get at is that a linear data structure is mostly sequential in nature, right? So that means the memories, the elements, all of them are stored in contiguous fashions, and therefore they are accessible in a contiguous memory locations. So what we are going to establish now is that in a linear data structure, the representation of a linear data structure and the representation of a non-linear data structure. Right, so this representation is sequential and mostly contiguous, right? But this is hierarchical. So that is the main difference that is coming out as far as representation is concerned, right? So next, what we are going to cover is the next one of the other important points of the linear data structure and non-linear data structure, which is on the traversal part of it, right? So the traversal part of it is in the single direction for a linear data structure, right? It is in a single direction for a linear data structure, whereas we have multiple paths here. On the other hand, from a memory utilization perspective, memory is mostly utilized in a contiguous manner. And here the memory is mostly non-contiguous, right? And of course, your examples will be your, from a linear data structure standpoint, it is queues, linked list, arrays, and from a non-linear data structure standpoint, it is graphs, trees, etc. So that's the solution to the question that you see here. Moving on, this is the last question in this series. So it again talks about the same thing. That's why I said we'll spend some time on the column major. Here it says both in row major and column major, give me the location, right? So if I want to do this in the same fashion, and because this is a zero index basis, so you will understand that on a zero index basis, we just now established a formula that the column major, in a column major, the formula is what? The formula is that we will take M, multiply it by J, and add I to it to get the number of bytes that we have to, or number of positions that we have to skip. Right? So to access an element I comma j, we have already established that in the previous example. If required, please rewind and go back to that position to probably see that. So M plus J star I. Now in this case, what is my M? My M is 5. My J is 7. My I is 2. And my my N is 7. N is 7 and J is 4. Okay, so if this is how it is, then from here, can we actually get to a position where we can say or apply this formula? What does this formula say? 5 into J, which is 4, plus I, which is 2. That means 22 positions have to be skipped, right, to reach to A24. Now 22 positions means 22 into 4 bytes. Why? Because we are talking of integer array. Okay, and therefore 22 into 4 is 88 bytes have to be skipped. From where? 88 bytes have to be skipped from the base address of 4000. So when you represent a 2D array in memory, we have discussed that how it flattens out in a column measure form. This address is already given as 4000, right? So if you see, this is the base address given to you. If this base address is given to you, then you have calculated that to reach A24 you have to skip 88 bytes. Therefore your position of your target element is at 4088 in memory. That is the answer to the first part of it. That is the column measure part of it. For the row measure, we don't know the formula because we have not calculated the formula, derived the formula. So let us derive the formula first, and then this will be easy. So for the row measure, what we will do is, we will take another array, which is a 2D array. We'll take 4 here and we'll take 3 here. This is 0, 1, 2. This is 0, 1, 2, 3. We will flatten it out in memory and we will say row measure means this is going like this, then like this, then like this, right? And we want to access, let's say, this element. So in our case, our M has become 3, N is 4, I is 1, and J is 2, right? So if you have to represent this in memory, so we'll go to 0, 0 first, going to the right because it is row measure, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, 2, 0, 2, 1, 2, 2, 2, 3. What is the index? Zero based indexing, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Where do we want to go? 1, 2. That means we want to go here. How many rows do we have to skip? We have to skip 1 row. Where is this one going to come from? Obviously from my I. I represents my row, so I will take the help of I. I will skip that row, but in each row, how many elements we have to skip? How many columns we have to skip come from the column? Where does this column come from? It comes from my, it comes from my N, right? So my column will come from my N. 4 columns I have to skip. So N star I. N star I means 4 star 1, which is equal to 4. Right? So I have skipped 4. I have to go to 6. So I need 2 more. Where do I get that? From my J, because now I am moving the columns here. 2 columns I am moving here, right? So I am going to take the help of J. So this becomes the formula N star I plus J. So that leads me to, now if I apply that formula here, A57, then what do I get? This is my position of an arbitrary element ij, right? Now I am applying the formula which is 2, 4, right? I is 2 and that is 4. Now if I eliminate all of this, just to make sure you don't get confused, I will eliminate this also and eliminate this also. So I have my formula. I have my M as 5, N as 7, I as 2, J as 4. So my N is 7 multiplied by I plus J 4. So that is my 14 times 4, right? So 56 is what is coming to in terms of the I'm sorry for that, there's a mistake here. Okay, so we will do 7 from n, yes, then we will do I, which is 2, then we will do j, which is 4. So we have 7 to the 14 plus 4 is 18. 18 positions will have to be skipped. This is equivalent to 18 multiplied by 4, that is 72 bytes will have to be skipped. From where? From my base address of 4000. So 4000 plus 72, 4072 is the position, and that is the answer in row major fashion. So that is the answer for this A problem, and the B problem that is there is on the define a sparse matrix. A sparse matrix is a matrix where most of my columns, most of my cells are actually having zeros, except for, let's say, 2 or 3 cells. So this is actually a sparse matrix. Most of the columns will be, so the number of elements which are not 0, number of elements which are not 0 will be very less than the total number of elements, right? So that is what is a sparse matrix. So that brings me to the end of this lecture. I hope this has been useful, and I've tried to cover it by keeping it in sync with your syllabus, by keeping it in sync with what kind of questions typically come in the course curriculums in most of the universities, and I hope that has been useful. We will cover the second part of this video lecture, which will cover module 1 from an algorithm standpoint, the time complexity and the searching and sorting part of it in the next video lecture of this particular series. Till that time, have a nice time. Goodbye. Thank you.